Okay, so I'm Mike Droettboom. I'm a data engineer at Mozilla. And today I'm going to talk about a project we're working on there called Iodide and a sub-project of that called PyData. This is the rough agenda. We'll talk about Iodide, then I'll tell you what PyData is, and then the Iodide server and how that relates to everything. And then if you stay all the way to the end of the talk, we have a very fun little toy demo. This is our team. We've got 5 people at Mozilla, and then we have some outside contributors at academia and in industry. We want to grow this slide with people here, hopefully. Okay, so what is Iodide? Came out of a problem we had sort of internally at Mozilla, where data scientists were doing experiments in order to answer some business question or some technical question about Firefox. And they would share that with their manager who makes the decisions. The decision would be made, and then all that stuff would just fall off a cliff. And then you repeat, right? So there's sort of this broken cycle. Things get built, explained, and then thrown away, where it would be much nicer to have a cycle that sort of connects all of the different phases of data science, the exploration, explanation, and collaboration, and keeps it going all in one system without any friction between these things. This sort of diagram is not my own. It's shamelessly stolen from a paper by Adam Rule and others called Exploration and Explanation in Computational Notebooks. And one of the interesting insights in that paper is that many analysts simply choose to explain and share their analyses using other more established media and provide a link for the curious back to the notebook where they performed the analysis in the first place. So clearly the tool is not supporting all of the things they need to do, or it's making it too hard to do all of the things they need to do in one tool. So we're trying to build something that's a little more akin to that. So what's the primary difference between our tool and something like Jupyter? Let me be clear right up front, we're not trying to replace Jupyter. We're exploring a different sort of trade-off space, right? Trying to make something that's different and explore what happens if you have a different set of trade-offs. What does that help? What does that hurt? So on the left, this is a diagram stolen from the Jupyter documentation. You may all be familiar here. You have a graphical user interface in your browser. It communicates to a server. That server communicates with a kernel, and that's where the actual data science computation happens. And the kernel is usually connected to some remote data source or maybe a local data source, right? So that's what you may know. What we've done in Iodide is we've moved the kernel into the browser. So all of the computation is happening in the browser. It puts you right next to the UI. It means you can do very interactive, low latency kinds of things with the UI in the browser. And then we do have a server to allow things like collaboration, data archiving, other things, but it's totally optional. I think it's going to be very important because it supports a lot of use cases, but it's not critical in order to run an Iodide notebook. So when you have these two different models, what you get with Jupyter that you're probably familiar with, if you want to share a Jupyter notebook with someone remotely, state of the art is to deploy it in a container using Docker or something and using Binder. This stuff is all way better than it was a few years ago, but it's still a cost, right? Because you're running a remote service on someone else's behalf. There's free services to do that. They don't always scale. If you're doing it internally, that's a big cost to your IT infrastructure, right? And if you're going to share a notebook locally, that person you're sharing it with is going to have to go install Anaconda, install Jupyter, all the dependencies. There's a lot of computation there, or sorry, complication there. The Iodide model is you basically, if you want to share something with someone, you put it up on a static web server. Every enterprise I've ever come across is running a static web server somewhere. That's a pretty low-cost thing to do. And if you want to just give someone the file, you can do that, and they just open up in their web browser. Now, obviously, the downsides here is your data's got to be pretty small, your computation's got to be pretty simple. But if that's okay with you, we're in this different trade-off space, and I think it creates some interesting opportunities. Another major design feature of what we built is this thing called JSMD, which is shamelessly stolen from things like MATLAB cell mode or R Markdown. The JupyText project is also going in this direction, which is rather than using JSON like Jupyter Notebooks use, we're using a plain text format. So this lets you put it in Git pull requests work, all that tooling around standard text files works really well. Many of our users, we've found actually, they don't like to use the cells in the notebook. They just open these things up in their text editor of choice, and it all just works. Okay, so I'm going to do a quick demo of that. This is what an Iodide notebook looks like. It's communication first. This looks like a blog post or a document, right? It has this explicative text. You can put math in there. And then generally you'd have something interactive, an interactive visualization. Here we have a Lorenz attractor demo. All the computation is here is happening in the browser. I can change some of the parameters. And all this is very low latency because there's no server it's going to. It's all happening right here. But then beyond just this acting like a blog post, there's this Explore button up here. I push this, it's like view source. If you remember the old days of the web in the 90s with GeoCities and what have you, you could view source on things and you could actually, like that was how you learned how to put new things on the web. We're trying to bring that sort of ethos into the data science world and into the modern age. So here you can see on the left, there's this is the code, it's in cells, there's markdown with JavaScript. I'm going to get to the JavaScript issue in a sec. But this is basically all the things that created the page. On the right-hand side, we have a console that behaves very much like Firefox dev tools. You can look at the value of variables and play around here and inspect things and see what they are. All these little tabs kind of move around. It has like a little layout engine stuff. So anyway, it's this neat little development environment. So the idea is you might come across a notebook on the web. It does something almost what you want to do, or you want to drill down on the data in somewhere. You would hit the Explore button. Bob's your uncle. You have a full development environment here. You just keep going. All right, so I'm going to pop back to my slides. So everything I've talked about so far is, because we're in the browser, it's built around JavaScript, right? JavaScript has a real love-hate relationship for me personally. I mean, on the one hand, it's really fast. It's got probably the best compiler technology of any dynamic language out there. You can write things, it's in a lot of cases as fast as what you would write in C. That's great. On the other hand, you have these really legacy rough edges. The numerics in JavaScript aren't great. The typing isn't great. Like a lot of things you have to learn not to touch in JavaScript. And you do okay if you learn what not to do. It's familiar to a lot of programmers. The body of JavaScript programmers is huge, but it's not very familiar in this crowd, right, to data scientists. There are data scientists who use JavaScript, but it's not the big mature ecosystem like Python has, or R has, or Julia even, right? So that led us to the creation of the PyData project. PyData is basically a compilation of standard upstream C Python with NumPy, Pandas, Matplotlib, other data science tools to WebAssembly. Now WebAssembly, if you're not familiar with it, it's a fairly new technology in browsers. It's a bit code for compiled code that you share on the web in your browser. So it's a completely portable, but once it hits your browser, it gets compiled into native code, and it runs really, really fast. There is some related projects here. This is the first project I'm aware of that really is data science focused and tries to get the data science stack working really well. But there's a PyPy.js that brings PyPy into this environment. It has the same pros and cons that PyPy has, right? There was Zero Dependency Python, which was an attempt to do this with Google Native Client. Google Native Client has sort of been subsumed by WebAssembly. It's basically dead. So, and then there's Brython, which does something different. It actually transpiles Python into JavaScript and then runs it. So it's not a proper upstream C Python. You wouldn't get NumPy. You wouldn't get those other things. So I will pop over again and give you a demo. Here I have an Iodide notebook. And all you have to do to use Python, we have a little cell type drop down here. You can say JavaScript or Python, change it to Python, run this cell, and over here on the right you see it says loading the Python plugin, and a second or two later you have a full Python. Hold on, I'll make this a little bit bigger, I think. There we go. And what's really cool here is all of the data types sort of automatically convert back and forth. So if I have this Python data structure and I return it to display it, it's getting converted to JavaScript. And then the Iodide tool here is just displaying it as if it's JavaScript. It doesn't actually know anything about Python, but it's able to display these things because it's converting the data types. You actually have access to the entire DOM API of the browser from Python, which is really powerful. So here I have a little cell in Python that's going to make a little button and a little div, and when I click on the button, it'll increment the value. Right? So there's a little callback going into Python, adding to the number, coming back. It all kind of magically works. You could use this to like rewrite Facebook entirely in Python if you wanted to. I don't recommend that, but you literally have everything. There's no shortcoming here. Another fun little demo you can do is you can make a canvas and hook up all the mouse events to like draw on the canvas, and that's all happening from Python. This is also the basis for how we get matplotlib to work, which I'll show in a sec. So that's all pure Python I've showed so far. If you import NumPy, it's going to go out to the network, fetch NumPy, bring it down, and then it displays the numbers. So I just made a little sine wave here, right? It's not great to see a sine wave as numbers. What you want to do is plot it, right? So this cell, import matplotlib. It's going out, importing matplotlib, all of matplotlib's dependencies.
When you say going out,
it's going out over the internet.
Yeah, it's pulling your libraries
from what's currently hosted on GitHub pages.
Oh, okay.
But yeah, just from an HTTP website. And once you've actually done this, for demo, I wanted actually you to see the time. But once this happens, once it gets cached in your browser, and it's just really zippy the next time.
It would never be embedded in one of these notebooks, but it would be loaded per user one time.
Exactly. Yeah, exactly. And so when you, oh, here we go. Got to scroll down. So here's matplotlib. Let me make this, the screen is a little small here, but basically you have a full matplotlib plot here of the sine wave, and it's fully interactive. So all of this back and forth is happening without a round trip to a server, right? All entirely within the browser. And so that's really cool. You've got like the bones of the Python scientific stack here. However, because the data is actually shared back and forth between Python without even copying it, if you want, you can mix and match things. So I can take this NumPy array I've made and import Plotly, which is a JavaScript plotting library, and plot it in Plotly. So if you prefer Plotly, it's nothing keeping you from using that instead, and it works just as well. This, of course, is interactive too. But here they've written the plotting library in JavaScript. So it's very tightly coupled. I think that's sort of one of the coolest parts about this. So I will pop back to my slides. Biggest question I get, how fast is it? This is a set of sort of NumPy numeric benchmarks that someone else wrote. And you see some variation there. The scale here is how many times slower it is in the browser versus native on the same machine. So worst case, it gets to be about 10 times in Firefox. Chrome is still significantly slower. Hopefully I assume they will catch up at some point, but they are playing some catch up. And the thing that seems to make the difference between the things that are like 10 times slower and the things that are the same speed is how much Python work you're doing. One thing that is slow in WebAssembly is calling a function pointer, and that's for security reasons, which I don't even fully understand to explain, but they have a little extra work they have to do to call a function pointer, and because the Python interpreter is basically a function pointer calling machine, that's what it does. The more Python stuff you do, the slower it gets. However, these benchmarks down here, they're mainly working in NumPy, and so they're like tight C loops. And they pretty much are at par, so that's pretty cool. What doesn't work is actually pretty obvious. The Python test suite is running, and for the most part is working just great. But things that you can't do in a browser, you can't do with this either. So you can't open up a raw network socket and start serving things over it. You can't fork a subprocess, because we don't have subprocesses in the browser. And you can't access files on your file system, right? threads and asynchronous stuff are coming. That's not in WebAssembly MVP level, but there are plans to build that. So eventually someday we'll get multi-threading. In this, you can use web workers now and do some things, but there you're building specifically for the browser, and it's hard. So where do we want this to go in the immediate future? These are the packages we have. We have Python and NumPy and Pandas and Matplotlib. If you go down the list of the most popular scientific Python packages, the next on the list are really scikit-image and scikit-learn. But those both depend on SciPy, and SciPy depends on Fortran. And it's a little dirty secret of this community that we're relying on software using one of the oldest extant programming languages around, okay? And so the story of compiling Fortran to WebAssembly isn't really fully there yet. It's not good enough to compile SciPy, so we're gonna have to push on that and move that forward. But once we solve that, hopefully we can also get R. So a big part of where we wanna go with this is having this nice, tightly integrated system where you can do some of your stats in R where it's really good, and do some of your data munging in Python where it's really good, and not really care, and do that all in the same process within the browser. The key around that, of course, is something like Apache Arrow or libnd type in the middle as the sort of conversion layer to help you move those data types around without any copying. But already we have a few other languages, not just Python. Outside contributors have given us Ruby, OCaml, Lua. These JavaScript-related languages are obviously really easy. So we have JSX from React and TypeScript. So it's growing already into kind of an ecosystem here. The other thing we want to do is extend Conda Forge. So right now, Conda Forge builds for Linux, Mac, and Windows. We're going to add a fourth one called WebAssembly. And that will hopefully make it a lot easier to get new packages into this thing, and it won't be a bottleneck on a handful of developers to add new packages. We also already, and I don't have a slide for this, if you have a binary wheel of a pure Python package on PyPy, you can install it. It just works. Nice. So go wheels, they make that easy. All right, so that's PyDide. I just want to check my time. Okay, so now I'm going to talk about the server. Now, like I said, this is an optional feature, but I think it turns this from a thing that's kind of a cool toy into a real professional collaboration tool. So we want to build a real Google Docs-like experience where you just edit and things are saving, and you don't have to care about remembering to save. Just keep that, the thing that everyone knows from Google Docs, where you don't care about that stuff. Make it easy to share, add commenting, collaborative editing, forking, all these nice things that Google Docs is sort of the shorthand way of saying that. And a place for archiving and exporting your notebooks, as well as your data. I think when you have data scientists all managing their own stuff, sometimes it's a little tricky for collaboration, but whereas if you have a centralized place to share and work around, that's basically what the server is going to handle. The server also acts as sort of a data broker. There's many times where in the browser you can just hit an HTTP URL and get your data back. You have some data service or whatever. That doesn't always work. Sometimes there's an authentication thing you need to do in the middle, and the server will help with those sort of cases and act like a broker or a connector to various data sources. So now I'm going to invite my coworker Tion up here, and maybe you can explain what this is while I get the demo going.
Sure. So in a former life, I was a neuroscientist, and I actually specialized in neurophysiology. So this, what we have right here, is a portable EEG. So this is connecting over Bluetooth. It's pretty cool. It's no longer the case that you have to go into a lab, get hooked up with electrode in order to have your brainwaves read. So this is pretty cool. It's $200. It's from Muse. It's a great company. So have we turned it on?
Switch it on, yeah.
Okay.
So we're connecting to the headset using a technology called Web Bluetooth, which lets your web browser communicate over Bluetooth to all kinds of crazy devices.
This is so dangerous.
Yeah.
Sorry.
But you can do it.
Yeah.
Upload your brain to the web.
All right. Okay. We're having the same issue we had the other day. Sometimes this glitches out and it doesn't connect the first time. I'm gonna reload the page.
Somebody else's Bluetooth
Yeah, that's right. Everybody, if you have one in the audience, please turn it off. All right. I'm gonna restart. This worked last time at least to restart it, so haven't gotten to the bottom of where that issue is, but. Okay, we'll reconnect. Won't let me. Damn it. There we go. It's not letting me click the button. All right. One more time. One more time is the charm, right? So, and to talk about what this notebook is doing, it's taking the Bluetooth data from the headset, bringing it into Python, performing an FFT over there, because we have FFT in NumPy, and then plotting that out again using matplotlib. So it's a real like hybrid of all the various technologies here.
And what EEG does, it measures the voltage on the scalp. So you can think of this as a multi-volt meter. And you basically have a reference, and then you have...
We have data coming. Put it on
Okay.
your head. We're just getting noise right now. Try not to think too much, so we get a nice...
It's very tough. Let me see.
Yeah.
I can try.
There you go. So you're seeing the top 4 lines are the 4 EEGs, the 4 detectors on the device.
So we have-
the bottom one is the FFT.
We have TP9, we have AF7, AF8, TP10. So these are the frontal electrodes. These are the ones around the temporal parietal. And what's really cool, this is also used for meditation. So one thing that we know from meditation is that when you are being very attentive, very focused, you have an increase in the alpha range, which is between 9 to 12 hertz. So there's oscillations that happen in the brain. And between 9 to 12 hertz, when you are meditating, you see an increase of power. So what you will see in the FFT is that the values go up when you're meditating versus when you are talking or just doing other things where you don't have a singular focus, where it's down.
Cool.
Yeah. Live demo. Yeah.
Yeah. All right. So I just got 2 more slides, and then I think we'll have some time for questions. All right. So part of us coming here, we're Mozilla. This is all open source. This isn't really a sales pitch at all. This is actually a call for contributions. We need experimenters, designers, programmers, writers, bug hunters, anyone who's interested in helping us out. Find us on GitHub. That's our GitHub project. We are also having an unconference space at 4:30 in Belasco, way down around the corner. And yeah, and there's my email. So that's it. I'm ready for questions.
This is great, wonderful work, and really inspiring stuff. You mentioned that right now the biggest performance bottleneck is doing kind of native Python operations, and you also mentioned that as opposed to some other libraries, there's not any transpilation happening. Have you considered transpiling easily transpiled bits of Python into JavaScript or WebAssembly?
So I haven't played with that at all. I mean, I have played with the Python package and demos, and the thought of rebuilding a NumPy that would work in that environment sort of put me off and thought this might be a faster path to all the data science stuff. But you're right, there may be some sort of hybrid approach in the middle there of like transpiling some of it and getting it to connect. I haven't experimented with that at all, yeah.
Thank you. Question, you said we couldn't get raw sockets, but can we get web sockets, and can we get them today?
Yes,
Then-
yes, you can get WebSockets. But you have to have something that speaks WebSockets at the other end. Yeah.
Hello, Mike. I really liked the format of the Jupyter, like plain text. That doesn't have the output, or it's plain, because what you showed was only the input, right?
Yeah, so actually it was input on one side and the output in another pane. We actually, in an earlier iteration of this, we were more like Jupyter where we had inputs and outputs interleaved. And just from the user community within Mozilla we had, the feedback was that that was, for a tool that's about building a report, that actually got to be really confusing because at a certain point you're trying to have things be up here, but your code is down here. And so it was much easier to just do it side by side and more like a console thing. And my understanding is this is what MATLAB does. This is what our studio does this too. So that's the model we've gone with.
And internally in the text file, is it store everything, input and output, or is it separated? Is it in two folds?
It doesn't store any output in the text file. It's just input. The premise is that you can always generate the output because you're always going to be in a browser environment. Yeah.
Good. Thank you.
Sure.
Yeah, I think this is really cool. Have you tried using F to C to compile those bits of Fortran?
Yes, and actually F2C gets us pretty close. Unfortunately, F2C only supports Fortran 77, and there is some more recent Fortran standard stuff in SciPy and R. So again, like I think the last commit to F2C was sometime in 2002 or 3, so it's kind of a static project. But it would be there's all kinds of ways we can hopefully move it forward. I think there was a question up here if we still have time. Yeah.
How easy is it for somebody to replicate your demo? How easy is it for someone to replicate your demo? Is it on your laptop? Is it? I missed the initial part. Is it on the cloud?
Yeah. So yeah. I did everything locally on my laptop because I always worry about conference Wi-Fi, but many of these demos are actually already available online at iodide.io. Unfortunately, it's an older version of our thing, but you can just visit it there and hit it with your browser and play with it yourself. Yeah.
So I have two related questions. So the first one is, if I have a command line application, how easy is it to like get a terminal that then you can use the command line application from? And the second question is, say I have a rich client application based on Qt or whatever, how easy is, what happens when you go and try to load those tools? Where do they get rendered and what happens there?
So with the command line application, I haven't put any effort into trying to get like standard in and standard out working. So standard out kind of works. If you say print from Python, it prints to the JavaScript web console, right? If you open up the developer tools, that's where it comes in. And actually, the default behavior is if you read from standard in, it pops up a little dialog. If you've ever seen javascript.alert, that really old school thing, pops up a little dialog where you can type things in. So that's what works now. Not really what you're talking about, but the pieces are all there to probably build something like that. We haven't put any effort into it. My understanding is that Qt has a WebAssembly port that's being worked on. So if you put it together with that, theoretically, there's a big splashy demo of AutoCAD running in the browser, which is like an old traditional desktop application. And so it can be done. It's just how much effort it is hard to say. Yeah.
Perhaps a very goofy question, but do you envision, like, once you have a scikit-learn there, would you envision some parts of machine learning production being moved to the front end using this technology? Say recommendation systems or carousel?
I think it's hard to say. So I think where the sweet spot of this is like for a notebook where the Python is exposed to the user, like that's where I think this is really interesting because you have a really good reason for Python to be there, which is that it's the user interface to what you're trying to do. For things that like are in production that maybe work in a different environment, this is not going to be the most efficient way to do that. It might be the most developer efficient way, and so there's that trade-off. But yeah, I don't really know, but it's an interesting space to look at too.
A lot of the tooling, I guess, is written in Rust and then like the transpiled or compiled to WASM or WebAssembly.
So no, it's all like it's literally the C Python source code that gets compiled to WebAssembly. There's no Rust in here yet. We'd like to have some Rust support, but it's just the upstream projects recompiled with a few patches to make it all work.
And is there any projects you know of that are looking at targeted at being able to compile like Python to WASM, or I guess is this kind of what it's?
Yeah. So this is basically interpreting Python in the traditional way that CPython does, but inside the browser. Brython is something that compiles or converts the Python to JavaScript. So it's a different approach. It ends up being less like standard Python and a little less complete, but who knows, with more work on that, that might be a really viable approach too, yeah.
Thank you, yeah,
Sure.
That was really incredible.
Thanks.
I think we might have time for one more.
Yeah. For Fortran compilation, for compiling Fortran, there's something called Flang that compiles it to LLVM IR,
Yes.
which goes to WebAssembly. Have you considered?
Yes. Oh yeah, we've actually been talking to the Flang developers, and they're very receptive in general to this idea. There's a little work that needs to be done. So Flang it uses a port of LLVM that's a little old. So the WebAssembly support is not great. So we need to kind of push LLVM from this end and Flang from this end and get them to meet in the right place. But the pieces are there, and it's hard to say how close it is, but we wouldn't have to start from scratch. Yeah.
Probably do one more. This one. Okay.
All right.
Yeah.
Thank you
very much. You'll be in Belasco later?